Today we're looking at a Java interview problem where we need to compute the exponential function. So x to the y. A few constraints with this problem. We're not allowed to use the built-in Java methods, so we can't just do x to the y. We can't use anything in java.lang.math, so we can't use something like math.pow. And a few other constraints we'll see. We need to implement the solution recursively, and also there are some interesting time complexity targets we need to hit. Let's get started. So our problem today is again courtesy of firecode.io. So reviewing the problem here, we receive a base and an exponent, and we need to raise the base to the power of the exponent recursively. And as mentioned, we can't use any of the exponent or math power utilities built into Java. We need to shoot for time and space complexity between log of n and linear time. And we need to be able to handle both positive and negative bases and exponents. So some examples here: input of 2 and 3, 2 to the third power is 8. Input of 3 and negative 1, 3 to the negative 1 power is 0.33. And negative 3 to the 3 is negative 27. So let's go to the whiteboard and sketch out a solution. So to make things easier, let's start off by simplifying the problem a little bit. Let's suppose that our exponent is always positive, so greater than 0. And let's start off by building a non-recursive solution first, and then we can make it recursive later at a next step. So an iterative solution then could just be to loop through exp number of times and multiply base by itself and return that result. So something like this: just start with 1, loop through exp number of times, and our result is going to be our result multiplied by our base, and then finally returning the result. So this is an iterative, non-recursive solution. A recursive solution could look something like this. Our base case here would be when exp is 0, in which case we just return 1. Otherwise, we return our base multiplied by our recursive call using base, but then x minus 1. This gets us a step closer to our final solution in that we have a recursive algorithm now. However, it's still the same running time complexity, since we'll be calling our pow method here exp number of times. It's no different in terms of running time than just having our for loop that we had earlier. So if we want to get closer to our order of log n time complexity target, we need to be a little bit smarter. So to do that, let's look at a little example. Suppose we need to calculate 5 to the 14. So our base is 5, exponent is 14. Well, in this case, that's just equal to 5 to the 7 multiplied by 5 to the 7. So if we were able to calculate the value of 5 to the 7, we could just take that value, multiply it by itself, and return the answer, which would be 5 to the 14. Now, breaking down each of these, again, similarly, this is equal to 5 times 5 to the 3 times 5 to the 3 times 5 to the 7. So in this case, we broke down 5 to the 7 into 5 times 5 to the 3 times 5 to the 3. So we can continue this process recursively, breaking down each of these computations into easier computations. Every time the exponent is even, we get this scenario where we just multiply the base times the exponent divided by 2 twice. When the exponent is odd, like breaking down the 5 to the 7, we would have 5 to the third times 5 to the third times an extra base because of the modulo of the exponent. We can continue breaking down the base times exponent in this case down to our base case here when the exponent is 0, in which case we can just return 1, which you already have up here. So translating this into code then could look something like this. We keep our base case the same. If the exp is 0, we just return 1. Otherwise, we calculate a temporary value, which is our base to the exponent divided by 2. Now, if exp happens to be even, we can just return our temporary value multiplied by itself, because that will be just base to the exponent. If our exponent is odd, then we can multiply our temporary value, multiplied by our temporary value, multiplied by an extra base. So for our example there of breaking down 5 to the 7 before, because 7 interdivision 2 equals 3, and we divide 7 by 2 up here, we're computing. In this case, temp would be 5 to the third. So we'd have to multiply temp by itself by an extra base to get up to our 5 to the 7. Finally, if we wanted to get rid of our constraint of requiring exp to be positive, we could just simply add another condition up here saying if exp is less than 0, and in this case, we can just calculate pow of base and negative exp, which would turn exp into a positive number, positive integer, and return 1 divided by that, which will give us our base to the negative exp. So let's take our code and submit it to Firecode and make sure all the tests pass. Okay, everything looks good. So let's have a look at our algorithm in terms of our time and space complexities, where our target was time and space complexity of the order of log of n, and n being our exponent. So the time and space complexity analysis is kind of similar for both. In our algorithm, we only do kind of fixed computations throughout. So we do some division here, some multiplication and division here, but there's no loops or data structures or anything that would cause us to do more than a fixed number of computations for every method call. Now it is recursive, so the next question is how many times are we going to be making the recursive call? So every time through, we divide our exponent by 2. So how many times can we divide our exponent by 2 before we get to our base case where the exponent gets down to 0? So the answer to that is log base 2 of our exponent. Log base 2 of our exponent is the number of times that the method will be called. Now in the case of our exponent being negative, we would make 1 extra call because that would be the case up here where we just turn it to positive and then take the inverse to return the final answer. So if our exponent is negative, we'd actually be doing log base 2 of the exponent recursive calls plus 1. So we're doing 1 extra recursive call to turn the exponent into positive. Either way, it's on the order of log of n. Hope you found this helpful. We'll see you next time.